So let's look at a couple more examples for this induction, and we'll kind of review the process here. So we're using mathematical induction to prove a statement is true for every natural number. And of course, the natural numbers are 1, 2, 3, 4, 5, up to, so on. And so the way we can do this, let's go back up to right here. So for each natural number, P of n is a statement depending on n. And we want to show that if we can show that these two statements are true, then P of n will be true for all natural numbers. So the first one is that P of 1 is true. So if we plug in 1 for n, we have a true statement. And then if we assume that P of k is true for some number k, then we can, if we can prove, then we want to prove that P of k plus 1 is true. So we're assuming it's true for some number beyond 1. And then we want to show that it's also true for the next number. And so if we can do those two things, then we have shown that the statement is true for all natural numbers. So this one is a very common one. So this is just if you add up so the last video we did the first in odd numbers. Now we're just going to do the first in numbers, in natural numbers. So we want to show that 1 plus 2 plus 3 plus all the way up to n equals n times n plus 1 over 2. So the first step is to show that this is true when n equals 1. So the left side, we're just going to have a 1. And on the right side, we're going to plug in 1 for n. So we have 1 times 1 plus 1 over 2. And of course, that's 1 times 2 over 2, which of course is 1. So this statement is true for n equals 1. And if you want, you do not have to do this, but if you want, you could see if it's true for 2, just to kind of, sometimes it might help to kind of see what this pattern is and what the statement is showing. So it could help if you do n equals 2, n equals 3. Just so you kind of get familiar with how these formulas are working. But it's not necessary. You only have to show that it's true for the first one. So then the next step is we're going to assume that this is true for some number, whatever number we want, but we're going to call it k. So assume that 1 plus 2 plus 3 plus up to whatever number k equals k times k plus 1 over 2. So we're going to assume that's true. And now we want to show that 1 plus 2 plus 3 plus up to k and then plus k plus 1. So we're going to go up to the next one. So we're going to find the sum of the first k plus 1 numbers. And so now what we're going to do is we're going to plug in k plus 1 in for k. So if we wanted the formula, assuming this formula is true, this should equal k plus 1 times k plus 2 over 2. All right. So all this formula says is however many numbers we have here, we're going to take that number, the last number, multiply by the number that comes next, and then divide by 2. And so if k plus 1 is our last number, we're going to multiply k plus 1 times the number that comes next, which would be k plus 2 over 2. Okay, so so we start with the left side and then see if you can manipulate it, rearrange it, however you want to say it, and turn it into the right side. So we're going to start over here. We're just going to do some algebra and then see if we can turn this into this side over here. So normally the first step to doing this is use your inductive hypothesis, which is this. We know that, or sorry, this. So here's our inductive hypothesis. And so this says the sum of the first k numbers is k times k plus 1 over 2. So we can replace these first k terms with k times k plus 1 over 2. And then, of course, we have k plus 1 right here. So, so we're replacing these k terms by this, and then we still have the k plus 1 that goes there. All right. So now it's just a matter of simplifying this and see if we can turn it into this. So let's find a common denominator. So k times k plus 1, common denominator, of course, would be 2. So we're going to multiply this one, this term by 2, and then the whole thing is over 2. In fact, we'll kind of break this up into 2 steps just to make sure we're tracking here. So we're not doing anything with this. We're going to multiply the top and bottom of the second term by 2. And so now we have the common denominator. And so we can just write this as one term. So k times k plus 1 plus 2 times k plus 1 over 2. And then what we can do, we have a k plus 1 in this term. We have a k plus 1 in this term. So let's factor out the k plus 1. And then what are we left with? In this one, when we factor out the k plus 1, we're left with k. When we factor out the k plus 1 here, we are left with 2. And there is the answer. So you're not getting down. So a lot of these on WebAssign, actually, I think all of these on WebAssign are multiple choice. But in any case, it's important to remember you're not doing this to get a numerical answer. So the answer is not going to be 6 or 10 or something like that. You are proving that two sides of an equation are equal, and so that's what we've done. So this is a little bit different. Might take a little getting used to, but it is important to remember that we're not solving these for an answer, or a numerical answer. All right, so we just showed this one, and these are just other, if you add 1 n times, that would equal n. That's kind of the definition of multiplication. If you add the first n numbers, the square of the first n numbers, that would equal this, and then the cube of the first n numbers would equal this one. So so those might help as you're going through the homework. If you might want to reference those. All right, so let's look at this last one. And so this one actually is a geometric sequence. And so 1 plus 1/2 plus 1/4 up to, so we're dividing each term by 2 and ending up at, for n terms, 1 over 2 to the n. Actually, this would be n plus 1. So there's n equals 0, n equals 1, n equals 2, n equals n. So we actually have n plus 1 terms here. So let's try for n equals 1. So that would be 1 plus 1/2. And that would equal 3/2. So here's our left-hand side. And this is another way you can do this first step. You can just kind of do the left-hand sides and the right-hand side separately. Then the right-hand side would be 2 minus 1 over 2 to the first, which would be 2 minus 1/2, which is also 3/2. So that's the right-hand side. And so these are equal. So there's your first step. Now so there's step 1. Now for the induction step, we're going to assume that this is true for n equals k. Or in other words, 1 plus 1/2 plus 1/4 plus up to 1 over 2 to the k equals 2 minus 1 over 2 to the k. So we're assuming this is true. That is our inductive step. And now we want to show that is true for the next one. So add in the next term. So we'll go up to 1 over 2 to the k. And then we're going to add in 1 over 2 to the k plus 1. And then that should equal, now plug in k plus 1 there, 1 over 2 to the k plus 1. All right, so same method here. Pretty much doing the same method for all of these. Start at the left-hand side and then see if you can algebraically manipulate it and into the right-hand side. So we have our left-hand side, and like always, here is our inductive hypothesis. So there is the left-hand side there. So what would we do next? These terms equal 2 minus 1 over 2 to the k. So we're going to replace those with 2 minus 1 over 2 to the k plus 1 over 2 to the k plus 1. Okay. So now let's see what we can do with these two. So 2 minus 1 over 2 to the k. Actually, what is the common denominator? The common denominator would be 2 to the k plus 1. This would be the bigger number of the two. So that would be the common denominator. So how do we make this denominator be 2 to the k plus 1? We need to multiply it by 2. Because of course 2 to the k plus 1 is 2 to the k times 2. So if we multiply this one by 2, we'll have the common denominator. So let's make this 2 over 2 to the k plus 1 over, or sorry, we're multiplying the top and bottom by 2. So 2 to the k plus 1 over 2 to the k plus 1. And so now we have the common denominator, so that we could, if you need to do this in another step, actually let's not, because we have the negative. So let's do we can just do -2 plus 1, and that would be a -1. So minus 1 over 2 to the k plus 1. And that's what we got. So there is our right-hand side. So we start at the left-hand side. So there's our left-hand side, and there's our right-hand side. Start with the left-hand side. Use your inductive hypothesis here to get that. And then it's just a matter of algebra. So with the algebra here, multiply top and bottom by 2, and then -2 plus 1 gives us the -1 over 2 to the k plus 1. And it is kind of an interesting fact. If you went up to infinity, had an infinite number of terms, what would the sum be? Well, it would actually equal 2, because as k gets larger, this gets bigger. So 1 over 2 to the 100, let's say 1 over 2 to the 1,000, as this gets bigger and bigger and bigger, that number is getting smaller and smaller and smaller. So this is approaching 0, or I should write it like that, approaching 0. So this would just equal 2 as you get infinite number of terms. But that's for another topic, another discussion. All right, so probably expect you have some questions as you go through this section. So feel free to email me, and I will help you out.